So you want to get a handle on computers, right? Maybe you've got some big tech project coming up, or maybe you're just, fascinated by these things that pretty much run our lives now.
Yeah, absolutely.
And you've probably thought about wading through all the dense textbooks and manuals, but honestly, who's got the time for that?
Exactly. It can be overwhelming.
We totally get it. So this deep dive, think of it as your express lane to the really essential stuff. Whether you're just starting out or you already know your RAM from your ROM, we're going to break down the core concepts.
And hopefully uncover some maybe surprising history along the way.
Yeah, definitely keep it interesting without getting totally bogged down in super technical jargon.
That's the plan. We've basically sifted through the history, the hardware fundamentals, the software basics, trying to pull out the really critical information.
Think of it as a guided tour, right? Focusing on the pieces you need to really understand how it all fits together in the digital world. So what's the roadmap for today? We're essentially taking a journey, starting way back with the earliest ideas about calculation.
Like really early.
Yeah, surprisingly early. And tracing that path right up to the complex tech we use every single day. Then we'll tackle the core components, the hardware you can touch, and the software that tells it what to do.
And even if you feel pretty comfortable with tech, I think the history has some genuinely fascinating twists.
Oh, for sure. And understanding how the hardware and software actually interact, that feels like the real key to unlocking it all.
It really is. Our mission here is pretty straightforward. By the end, you should have a solid grip on the fundamental building blocks of modern computing.
We'll see how those first mechanical ideas evolved, how we got to this intricate dance between the physical machine and the instructions, the software that brings it all to life.
Exactly.
Okay, let's dive in then. Where does this whole incredible story even kick off? Because like you said, it's way before electricity was even a thing.
Right. Our sources actually point us back to the abacus, that ancient counting frame with beads.
Oh, wow. Okay, like from ancient civilization?
Yeah, centuries BC. It's basically one of the first attempts to sort of automate calculation a bit, using physical things to represent numbers.
Okay, so fast forward quite a bit, but
Yeah.
we're still pre-electricity. Some really clever people start building on that. We get logarithms in 1614 from John Napier, and then the slide rule in 1622 from Robert Bissiker. Now, these are analog computers, right? How's that different from what we use?
That's a great point. Analog computers work by representing values using continuous physical quantities. So like the position of the slider on the rule corresponds directly to a number.
Oh, okay.
Modern digital computers, though, they work with discrete units, those famous ones and zeros, but those early analog tools, they were vital for engineers and navigators for, centuries.
Then, 1642, another big shift. Blaise Pascal creates the first mechanical digital calculator. That sounds like a fundamental change in thinking.
It really was. Pascal's machine used gears and wheels, actual distinct parts, to represent and manipulate specific numbers. So it's much closer, conceptually, to how our digital computers work underneath it all.
Okay, but things really started heating up. For me, anyway, in the 19th century with Charles Babbage over at Cambridge. This guy was thinking way ahead of his time.
Oh, absolutely.
In 1812, he comes up with a difference engine designed to automatically crunch numbers for polynomial functions, like calculating the arc of a cannonball or something.
Exactly like that. It was a huge step towards automating the creation of those complex mathematical tables needed for navigation, astronomy, things like that. But Babbage didn't stop there.
No kidding. Then comes the analytical engine in 1833. And our sources call this the first fully automatic calculating machine. That just sounds revolutionary for the 1830s.
It was conceptually groundbreaking. The analytical engine design included ideas like a central processing unit, he called it the mill memory, which he called the store, and even the ability to follow instructions from punched cards. Basically the core concepts of a modern computer.
But the tech just wasn't there yet to actually build it properly.
Precisely. The manufacturing capabilities of the time couldn't match his vision, but the ideas, they were absolutely revolutionary.
So we go from gears and levers to essentially a blueprint for a computer. Then the late 1800s bring in electricity. Herman Hollerith's punched card machine in 1890. We've all seen pictures of those, right? Big machines reading cards with holes.
Right. Hollerith developed that for the U.S. Census. It used electricity to detect the holes in the cards and automatically tally the data. It massively sped up data processing compared to doing it all by hand, a huge leap in efficiency.
And then, 1905, another absolutely critical piece falls into place. Lee De Forest invents the vacuum tube, the triode. This feels like the direct ancestor of modern electronic computing.
You're spot on. The vacuum tube could amplify electronic signals and, crucially, act as a switch, turning current on or off electronically. That ability to switch is fundamental to how digital computers work. It really paved the way.
Okay, stage set. Now we hit the war years, World War II specifically, a time of, well, intense technological pressure and innovation.
Definitely.
In 1935, IBM's 601 machine, using relays, which are basically electric switches, right,
Yeah.
hits 1 million operations per second. That already seems like a massive jump from purely mechanical stuff.
It was a big improvement. Relays were faster than mechanical parts, but the real electronic game changer was coming.
Right. The sources flagged the ABC, the Atanasoff-Berry computer, in 1939 as the first electronic digital computer. What makes it the first electronic one?
So John Atanasoff and Clifford Berry built this at Iowa State. The key difference was it used vacuum tubes, not electromechanical relays, for its calculations. It wasn't programmable like we think of today, but it proved electronic computation was feasible.
And then, in Germany, Konrad Zuse creates the Z3 in 1941. That's called the first programmable computer. How was it programmable?
The Z3 still used relays, but its instructions, the program, were stored on punched film tape. So you could feed it different tapes to make it do different calculations without having to physically rewire the machine each time. That's the key programmability aspect.
Gotcha. The early 40s are just buzzing. We get the Harvard Markhurst in January 43 from Howard Aiken. What was its role?
The Markhurst was another big electromechanical beast, funded partly by IBM and used by the U.S. Navy for gunnery calculations and other complex wartime math, another step toward automated computation for practical, heavy-duty tasks.
And then, December 43, Colossus. Built in secret at Bletchley Park in the UK, Station X as the source calls it. This had a very specific, very secret job, didn't it?
Hugely important and top secret. Colossus was instrumental in breaking the German Lorenz cipher during the war. It was one of the very first electronic digital computers, using thousands of vacuum tubes. Its existence wasn't even revealed until decades later, a massive wartime advantage.
Which brings us to 1945, and ENSE, the Electronic Numerical Integrator and Computer, University of Pennsylvania. This one gets called the first electronic general-purpose digital computer, and the specs are just mind-blowing for the time.
Oh, yeah.
30 tons, took up, 1,000 square feet, sucked down 140 kilowatts of power, and had 18,000 vacuum tubes.
It was an absolute monster, but incredibly powerful for its day. It could do about 300 multiplications per second. Its first big job was calculating artillery firing tables for the Army, a very concrete problem solved much faster than humans could manage.
And I could just picture the headlines in 1946, giant brain with blinking lights. It must have seemed unreal, but here's the catch. Programming it meant using a plug board. That sounds painful.
It was extremely tedious. Changing the program involved physically unplugging and replugging hundreds, maybe thousands of wires in a specific pattern. It could take days. This was a major bottleneck.
Yeah, you can see why they needed a better way. Which leads us right to that crucial EDV fake report, drafted mainly by John von Neumann in 1945. This basically laid out the architecture for almost all computers since, right?
Absolutely fundamental. The EDV-FE report proposed the stored program concept, the idea that both the instructions for the computer and the data it was working on could be stored together in the computer's memory. This architecture, often called the von Neumann architecture, was a revolutionary idea.
It meant you could change the program just by changing what was stored in memory, not by rewiring the whole machine.
Exactly. A massive leap in flexibility and efficiency.
And that perfectly sets up the next huge breakthrough. 1947, the invention of the point contact transistor at Bell Labs by Shockley, Bardeen, and Britton. This is basically the death knell for those big, hot, unreliable vacuum tubes.
Pretty much, yeah. The transistor did the same job switching and amplifying, but it was vastly smaller, needed way less power, generated less heat, and was much more reliable. It completely changed the game for electronics.
And just 2 years later, 1949, we see EDSAC, the Electronic Delay Storage Automatic Calculator built by Wilkes and Wheeler in Cambridge. Our source calls this the world's first practical stored program computer to actually be up and running. Von Neumann's idea made real.
Precisely. EDSAC successfully put that stored program concept into practice. A huge milestone. Its specs seem modest now, about 3,000 vacuum tubes, 500 kilohertz clock speed.
Still vacuum tubes, though, for EDSAC.
Yes, EDSAC still relied on vacuum tubes. The transistor was brand new, remember? But EDSAC had memory using these fascinating mercury ultrasonic delay lines, which the source jokingly calls early DRAM. It could hold about 10^24 words of 17 bits each.
And get this, it even had a tiny 31-word operating system. I mean, super basic, I imagine, but still, the beginnings of the software that manages everything today.
Yeah, very rudimentary, just handling basic input-output and loading programs, but still significant. Then, jump to 1954, Bell Labs again, with TREDIC. This is called the first electronic computer without vacuum tubes. So the transistor takeover begins. The transistor had proven itself viable. TREDIC showed you could build a whole computer using them.
And the innovation train just keeps rolling. Also, 1954, Texas Instruments makes the first silicon transistor. Silicon becomes a standard material. Then, 1959, another massive leap, the integrated circuit. Jack Kilby at TI and Robert Noyce, working independently, figure out how to put multiple transistors onto a single tiny chip of silicon.
Just revolutionary. The integrated circuit, or IC, meant you could make things even smaller, faster, cheaper, and more reliable. It really paved the way for the personal computer revolution decades later.
You start seeing them in machines like the IBM System 360 in 1964. Things are starting to feel a bit more modern. Then, 1971, Intel introduces the 4004, the first microprocessor. That's basically a whole CPU on one chip, right?
Exactly. Ted Hoff led that project. The 4004 packed about 2,300 transistors onto a single chip. It could perform maybe 60,000 instructions per second, kips. It made computers much smaller and more affordable possible.
A truly pivotal invention.
Absolutely.
And then names that might ring a bell for more people. The Intel 8086 and 8088 in 1978. The source notes these were used in the original IBM PC.
Yeah.
That's when computing really started hitting desktops and businesses and even homes.
Yeah, that partnership was key to the PC explosion. And by the early 80s, around 1980, we're talking about VLSI, very large-scale integration, chips with over 100,000 transistors on them.
And the density just kept climbing exponentially. The source mentions modern chips having something like 800 million transistors and running at speeds like 3 gigahertz. Just astronomical compared to ENIAC.
The progress is just staggering when you look back.
It really is.
Okay.
So that's the incredible historical arc. Now let's shift gears and focus on the fundamentals of how these modern machines actually work. Hardware and software. Our source starts with a key distinction. Data versus information. Data is just raw facts, right? Unprocessed stuff.
Exactly, like a list of temperatures recorded every hour, just numbers.
But information is when that data gets organized, processed, given context, made useful, like turning that list of temperatures into a graph showing the daily trend.
Precisely. Computers are essentially machines for transforming raw data into meaningful information. That distinction is really core to understanding their purpose.
Okay. Then we have hardware.
Yeah.
That's the physical stuff you can actually touch. The computer case, the motherboard inside, the power supply.
And all the tangible components.
And connected to that core hardware are peripheral devices. Your keyboard, mouse, monitor, printer, maybe an external drive. Things that let us interact with the main system.
They're the interfaces between the user and the computer's internal workings for input and output.
And the other side of the coin is software, sometimes just called a program. These are the sets of instructions that tell the hardware what to actually do. And the source makes a crucial point. Hardware without software is just, well, an expensive doorstop.
Pretty much. The software provides the intelligence, the step-by-step guide that makes the hardware perform useful tasks. One is useless without the other.
And this all happens within what's called the information processing cycle.
Yeah.
Could you walk us through those steps? Seems fundamental.
Sure. It's a 4-stage cycle, basically. First is input, getting data or instructions into the computer. That could be typing, clicking, scanning something.
Okay.
Second is process. This is where the CPU, the brain, actually manipulates the data based on the software's instructions. It does the calculations, the sorting, the logic.
Got it.
Third is output. Presenting the results, the process information back to the user, displaying it on the screen, printing it, playing sound. And fourth is storage, saving the data, the instructions, or the resulting information for future use, usually on a hard drive or other storage medium. And this cycle, input, process, output, storage, is just constantly happening whenever you use a computer.
Input, process, output, storage. Simple but powerful concept.
Mm-hmm.
So what are the main hardware components involved in making the cycle happen?
Well, the source breaks it down into 5 main categories. You've got input devices, output devices, secondary storage media for that storage step, the central processing unit for the process step, and memory, which is also crucial for processing.
Okay, let's maybe unpack those a bit. Starting with input devices and media, how we get stuff in. We know the common ones: keyboard, mouse, touch screens.
Right, but there are others too. Light pens, though less common now. Digital cameras are input devices. And then you get into some interesting areas like biometric systems.
Ooh, yeah, that sounds high-tech. Like fingerprint readers.
Exactly. Biometrics uses unique human characteristics for identification or verification. Fingerprint readers on phones are a perfect example. But there's also hand geometry systems, voice verification, signature verification pads, even iris recognition that scans the patterns in your eye.
Wow, okay. Pretty sophisticated stuff.
Definitely. Then you have sensors. These are devices that collect data directly from the environment, measuring temperature, light, pressure, motion. Like the example of a sensor monitoring a furnace temperature. They bridge the physical and digital worlds directly.
Right, and voice response units that can understand spoken commands and just everyday remote controls. Those are input devices, too.
Yep. Anything that sends data or instructions into the computer system. Now, optical readers are another important category. They use light to read marks, characters, or codes.
Like OCR, optical character recognition. That's the tech that lets you scan a printed page and get editable text, right?
That's the one. It uses a scanner and complex software to analyze the shapes of characters typed, printed, sometimes even handwritten, and convert them into digital text. Super useful.
And then OMR, optical mark recognition. That's for bubble sheets, like on tests.
Exactly. It detects the position of those filled-in marks by seeing where light is reflected or blocked, much faster than grading by hand. The source even mentions scanning an answer key first, so the machine knows the correct pattern.
Clever. And barcode readers. We see those everywhere, scanning the lines on products at the checkout.
Those lasers read the pattern of black and white bars, which represent a unique code identifying the manufacturer and the specific product, essential for retail and logistics.
And all that often comes together in a point-of-sale POS terminal in a store. It's not just a cash register anymore, is it?
Not at all. It's typically a combination of an electronic cash register, a barcode reader, a card payment processor, maybe a small printer for receipts, all linked into the store's inventory system. It captures the transaction, updates stock levels, processes payment, a key input and output hub.
Okay, so that's getting data in. How about getting information out? Output devices.
Right. The most obvious are visual display units, monitors, or screens, and audio output devices like speakers and headphones.
And printers, of course, for getting a physical copy. And plotters. What are those exactly?
Plotters are basically specialized printers designed for high-quality, large-format drawings. Think architectural blueprints, engineering diagrams, maps. They're more precise than standard printers for that kind of detailed line work.
Gotcha. Let's look at monitors' visual display units for a sec. The source mentions key features: color, monochrome, grayscale, or full color. Size, measured diagonally, like 15, 17, 21. And that size relates to a resolution.
Right. Resolution is the number of individual dots or pixels horizontally and vertically that make up the image, like 800 by 600 or 1920 by 1080. Generally, more pixels per inch means a sharper picture.
And the underlying technology. Older ones were CRT, cathode ray tube, those big, bulky monitors. Now it's mostly LCD, liquid crystal display, or similar flat panel tech.
Exactly. Those features determine the quality of the visual output.
Now, printers. They give us hard copy physical output on paper, unlike the soft copy on a screen. The main distinction seems to be impact versus non-impact.
Yeah. Impact printers physically strike an inked ribbon against the paper, kind of like a typewriter. Dot matrix printers were a common example.
Right, noisy things.
Yeah. Non-impact printers form the image without striking the paper directly. Inkjet printers spray tiny ink droplets, and laser printers use toner powder fused onto the paper with heat. Much quieter and generally better quality now.
And those plotters you mentioned, used for big drawings, engineering stuff.
Yes. They often use technology similar to inkjet printers, but they're built for much larger paper sizes and very precise line drawing. More expensive, specialized tools.
Okay, so we've covered input and output. What about the heart of the machine, the system unit? The source says this is the main box containing the chassis, processor, memory, bus, ports. But not the keyboard or monitor, those are peripherals.
Correct. The system unit houses the core processing and primary storage components. The engine room, basically.
And the engine itself is the central processing unit, the CPU, or just processor. This is where all the thinking happens, right? The calculations, the symbol manipulation.
That's the brain. Its main jobs are doing arithmetic and logical operations and directing all the input-output traffic. It has two key parts, the control unit and the arithmetic and logic unit. the ALU.
Okay, so what does each part do?
The control unit is like the director or conductor. It fetches instructions from memory, decodes them, and tells the other parts of the computer what to do and when. It manages the flow of data.
And the ALU.
The ALU is the calculator and comparator. It performs all the math addition, subtraction, multiplication, division, and it does logical operations comparing values, is A greater than B, checking conditions, is the result positive, negative, or 0. It handles the actual number crunching and decision logic.
So control unit coordinates, ALU calculates and compares. Got it. Now, memory. The source defines this as the electronic component storing instructions currently being used, the data being worked on, and the processed results. And there are two main types, RAM and ROM.
Right. RAM stands for Random Access Memory. This is where programs and data are held temporarily while the CPU is actively using them. You can write to it and read from it quickly. But, and this is key, it's volatile. Meaning when you turn the power off, everything stored in RAM disappears. It's like the computer's short-term workspace or scratch pad, sometimes called primary storage.
Okay. And ROM, read-only memory.
ROM is different. As the name suggests, you can generally only read from it. The user can't easily write new data to it. And crucially, it's non-volatile.
So it keeps its information even when the power is off.
Exactly. ROM typically holds permanent, essential instructions needed to start the computer up the boot process. That information is often burned in by the manufacturer.
So RAM is for active work, ROM is for startup instructions. The source also mentions variations like PROM, programmable ROM, which can be programmed once, and EEPROM, erasable programmable ROM, which can be erased with UV light and rewritten. So a bit more flexibility there for manufacturers sometimes.
Yeah, those allow for updates or customization after the initial chip production, useful in development or for specific product versions.
Okay. Now, what about storing stuff long-term, not just while the computer's on? That's secondary storage devices, right? Also called backing store or disk storage.
Correct. This is for permanent storage of your files, applications, the operating system itself. Unlike RAM, it holds data even when the power is off. The source distinguishes between the storage medium, the physical material like a disk platter or flash chip, and the storage device, the mechanism that reads and writes, like the hard drive itself.
And the main secondary storage device for a long time has been the hard disk drive. Uses magnetic storage, right? Capacities mentioned are like 120 gigabit to a terabyte, though they're much bigger now.
Yes, hard drives have been the standard. Advantages are huge capacity for the cost, and data stays put without power. Disadvantages: they're mechanical, so slower to access than RAM or ROM. They can fail the dreaded head crash.
Ouch, losing data.
Yeah, potentially damaging the disk surface and losing everything. And they're usually fixed inside the computer, so not easily portable.
Then we have flash memory cards, like SD cards for cameras, phones. These are non-volatile rewritable chips. Much more durable, right?
Yeah, very much so. They evolved from things like EEPROM, but are much easier to use. Being solid state, no moving parts, makes them great for portable devices that might get bumped around. Cameras, phones, tablets, even some laptops use them now.
And their cousin, the flash drive or USB stick, super portable, small, rewritable, basically a little circuit board in a case.
Yep. Advantages: tiny and easy to carry, hold a lot of data, way more than old CDs or floppy disks, pretty reliable with no moving parts, and they even became kind of fashion accessories sometimes.
True. Disadvantages: more expensive per gigabyte than a big hard drive, easy to lose because they're small, and sometimes the physical USB connector can get bent or damaged.
All valid points, but their convenience is undeniable for transferring files or quick backups.
Okay, that covers the hardware pretty well, the physical bits. Now the other essential half, software, the instructions. The source defines it simply as programs or instruction sets that control the computer's operation, and it splits it into two big categories: application software and system software.
That's the main division. Application software helps the user perform specific tasks. System software manages the computer itself.
So application software examples would be like word processors, Microsoft Word, spreadsheets, Excel, accounting software, Peachtree mentioned here, things you use to do something productive or creative.
Exactly. And application software itself can be categorized. Custom written, developed specifically for one user or company's unique needs. General purpose off-the-shelf software like Word or a browser that serves many common tasks. or special purpose packages also off the shelf, but for a more specific task, like a payroll system.
And the source notes that even off-the-shelf software can often be customized a bit to better fit how a specific organization works.
Right, tweaking settings, adding templates, integrating with other systems, that offers flexibility.
Okay, then the other big category, system software. This controls the computer's operations and manages its devices. Examples given are the operating system, utility programs, and translators, like compilers, which we didn't really detail but are important for programmers.
Let's focus on utilities and the OS. Utility programs are system software designed for maintenance and housekeeping tasks.
Like what?
The source lists things like disk cleanup tools to get rid of temporary files, antivirus software running in the background to find and remove malware, backup utilities to copy your important files somewhere safe, a corresponding restore function to get those files back, and personal firewalls to monitor network traffic and block unauthorized access.
Ah, okay. The essential maintenance crew for your computer.
Pretty much, yeah. They help keep things running smoothly and securely.
And then the big boss of system software, the operating system, or OS, like Windows, Mac OS, Linux. This coordinates everything the hardware does.
It's the fundamental control program. It has to be loaded into memory from the hard disk when the computer starts up before you can even run any application software.
Right, the boot process loads the OS.
Exactly. And once running, the OS manages all the computer's resources, the CPU's time, the memory allocation, access to disk drives, printers, network connections. It provides the interface for the user, and it handles requests from application software like saving a file or printing a document.
So its main functions are managing resources, providing a user interface, and executing application software.
That's a good summary. Resource management, user interface, and application platform.
And that user interface, how we interact with the OS and applications, the source mentions 3 types: command line, menu-driven, and graphical.
Right. Command line is the old school way typing specific text commands like in DOS or a Linux terminal. Powerful, but you have to know the exact commands and syntax.
Yeah, not very user-friendly for beginners.
No. Menu-driven interfaces present options in lists or menus that you navigate, maybe using arrow keys or numbers, more structured, easier than memorizing commands.
And graphical user interface, or GUI, that's what most people use now, right?
Yeah.
With icons, windows, mouse pointers.
Exactly. GUIs use visual elements, icons, representing programs or files, menus you click on, windows you can move and resize. You interact mainly with a mouse or touchscreen. Much more intuitive for most people.
Wow. Okay, we have definitely covered a ton of ground there, from like ancient abacuses and Babbage's gears.
All the way to integrated circuits with millions of transistors and sophisticated operating systems managing everything.
It's just a remarkable journey when you lay it all out.
It really is. And seeing how those fundamental concepts, calculation, programmability, storage, input-output, evolved through different technologies is pretty enlightening, I think.
Absolutely. So wrapping this up, what are the key takeaways we hope people get from this deep dive? We've traced that history, seen the major leaps. We've hopefully clarified the roles of hardware, the physical stuff, and software, the instructions.
And hopefully demystified that core information processing cycle input process, output storage that underlies everything a computer does.
Maybe there were a few aha moments, like the sheer size of ENIAC, or how early the stored program idea came about, or just how impactful the transistor and integrated circuit really were.
Those are definitely key points that often surprise people.
So why does this stuff matter? Well, whether you're just trying to understand the gadgets you use every day, or you need a foundation for work, or you're just plain curious, having this basic grasp of how computers work is pretty valuable, isn't it?
I think so. It moves you from just being a user to having some understanding of the principles underneath. It provides context.
And look, this deep dive is really just a foundation. If something specific grabbed your interest, maybe the early mechanical era, or the details of CPU architecture, or how operating systems function, there's so much more you could explore.
Absolutely. This is just scratching the surface on many of these topics.
So maybe a final thought to leave people with. Considering the absolutely breakneck pace of change we've seen, from room-sized machines to devices in our pockets that are vastly more powerful, what kind of fundamental shifts in how computers are built or how they work do you think might be coming down the pike in the next, say, few decades?
Ooh, that's a big question. Quantum computing, neuromorphic chips, deeper AI integration. It's definitely exciting to think about what the next revolutionary leap might look like, building on this incredible history we've just discussed.
Definitely something to ponder.